The time we took an image, we knew we were golden, that those stars had clearly moved.
The first order of business was to see how large the object is, to weigh it by measuring its gravity.
So we have the black hole here, and then the more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
Andrea's more advanced telescope made the difference. The object weighed in at a staggering 3 million times that of our Sun. But that didn't prove it's a black hole. It could still be a cluster of smaller objects. For the Germans, it was time to even the playing field. The VLT, Very Large Telescope, opened its doors on a mountain in Chile. Both the VLT and Keck were upgraded with revolutionary technology. For years, the teams relied on computers to pinpoint the location of stars through the turbulence of our atmosphere. Now, they could cancel it out with a new system known as adaptive optics. It uses a powerful laser beam to read the turbulence. Telescope operators can use those readings to sharpen the image of distant stars and galaxies.
So this little animation shows you the benefit of adaptive optics. So you see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxy. We track all of them, but these are the ones that are the key to the problem.
These new eyes were delivered just in time. With both teams watching, one of the stars made a dramatic hairpin turn around the center.
In 2002, it made a huge jump to over here. So it went whoop, all the way around.
The star was initially going very slowly and then moving around very quickly, and at that point coming very, very close to the central black hole.
And it's moving on order 10 million miles per hour, so it's just speeding away.
The star had come close enough for the teams to see that it had to be circling a single massive object.
All other physical explanations of what was at the very center were gone. The only thing left was a black hole.
To astronomers around the world, the evidence was impressive.
I have to say, when I first saw Andrea's video, I was stunned when I saw that star come out of the left side of the frame and go zipping around and go shooting off into the other end of the frame, and it moved around a point in space, and nothing was there.
That we could, with our instruments, together with our minds, effectively travel to the center of the galaxy, 26,000 light years away, and collect the evidence for such an incredible object was really an amazing achievement.
The European and American teams had confirmed that a black hole was there without actually seeing it. From our quiet corner at the far edge of our galaxy's spiral, it's hard to imagine the violence at its center. The closer you draw toward the center, the denser it gets. Our destination, the galaxy's central hub, brimming with stars, known simply as the bulge. Venture into the bulge and you enter a busy highway. It's jammed with star traffic speeding in every direction, and it's always rush hour.
There's a lot of gas. There's a lot of dust. This is absolutely the most crowded place in our galaxy.
There will be stars all around us, an incredible density of stars. I mean, we couldn't exist there. There's lots of ultraviolet radiation, X-rays are floating around, gas clouds bash into each other, a lot of activity. It's a very hostile environment, really.
The black hole is surrounded by a cloud of super hot gas that's falling in. The space around the black hole is so warped, it distorts the light that scatters across it. As bizarre as it seems, the gravity of a supermassive black hole is so spread out that you might fall in and survive for a moment.
During the final descent, you would then go into the event horizon, but you would actually not feel it because you are a small body compared to the large, massive black hole.
Now, thanks to a computer simulation based on Einstein's own equations, we can visualize the scene. As you move toward the black hole's core, you hit an inner horizon, a logjam of trapped light and energy.
At a certain moment, as we hit the inner horizon, there's this infinitely bright, blinding flash of light. That's all the stuff that's been waiting there, trying to get out, is just held there at the inner horizon. It would vaporize you. Almost certainly, if you fell into a real black hole, you would simply, unfortunately, die.
But that's not the end of the journey. The computer storm can be turned off, and the strange predictions of Einstein's equations allowed to play out. A passageway opens up, a tunnel through space and time known as a wormhole. We now leave through a strange door known as a white hole. Here, the twisted logic of extreme gravity goes into reverse. Instead of being sucked in, you would be catapulted out to the far reaches of time and space. But to where? In science fiction, wormholes offer handy escape routes to other universes. In reality, the inside of a black hole is probably too chaotic and violent for a wormhole ever to form. The black hole at the center of the Milky Way is strange enough as it is. But is it the norm? Or is our galaxy a freak of nature? To find out, astronomers have mounted a major international project to search galaxies throughout the universe for evidence of supermassive black holes. From Apache Point in New Mexico, astronomers are probing big galaxies out to 1 billion light-years from Earth. They take a series of steel plates and drill holes to exactly match the location of galaxies in the night sky. Then they plug fiber optic sensors into those holes, and for the first time ever, they can use the plates to capture the light of hundreds of galaxies per night. The astronomers are looking for a distinctive light signature coming from a galaxy's core. It's a sign of hot gas swirling into a black hole. The goal of the project, called the